As we know from our basic functions, the graph of y equals x squared looks like this, y equals x cubed like this. I've indicated where x equals 1 and y equals 1 on each of these graphs, and then we've kind of enlarged the region between x equals 0 and 1 and y equals 0 and 1. Each graph, of course, goes through the point 1, 1, and the reasons for that are very clear, and through the point 0, 0. At x equals 1/2, x squared is equal to 1/4. So we take the interval from 0 to 1, cut it in half, and cut that in half, and we have 1/4, and plot the point accordingly. For x cubed, of course we have the point 0, 0, and 1, 1 as before. When x is 1/2, then x cubed, as we know, is 1/8. So we have the interval from 0 to 1, we cut that in half, and we get the 1/2 point, y equals 1/2. Cut that in half, we have the y equals 1/4, and cut that in half, we have the y equals 1/8 point, and that point is plotted here, where x equals 1/2. So we see the graph looks like this. Now, since we've moved this point twice as close to the x-axis, the graph is flattened out a bit. And it also, in order to get up through the point 1, 1, it has to become steeper. So it's steeper at 1, 1 than this graph. And of course, we understand in terms of the overall graph why it has to be steeper at 1, 1, or why, we feel like it needs to. If we got to x equals 2, the x cubed graph has to go all the way up to 8. The x squared graph only has to go up to 4. So this graph certainly has to be steeper between here, between x equals 1 and x equals 2 than this does. And it pretty much follows that it has to be steeper when x equals 1 than this one does. And that's consistent with what we see over here. Now, if we go to x to the 4th, well, let's think about why is this graph symmetric with the x-axis, and this graph is symmetric with respect to the origin. And I said the x-axis. This graph is symmetric with respect to the y-axis because one side is a reflection of the other through the y-axis. This is symmetric with respect to origin. Any point out here, you draw a line from here to the origin, and then along the same direction for the same distance, you get a point down here on the graph. Well, now, why is this symmetric with respect to the y-axis? We go back to the table, and we should clearly understand by now that when you square the negative numbers, -2, -1, -1/2, you get the same thing you get if you square 2, 1, or 1/2. For x cubed, if we square the negative number, it's going to be negative. So that when x is negative, our y values are going to be negative. They're going to have the same magnitude they would on this side, but they're going to be negative. So what's going to happen if we go to x to the 4th? Well, one thing that happens is the graph becomes symmetric with respect to the y-axis again. If we square or take the 4th power of a negative number, well, it's an even power. If you multiply 4 negative numbers together, you're going to get a positive. So we have the symmetry with respect to the y-axis. And also, this graph is going to be even flatter than this one. If we just look between 0 and x equals 0 and x equals 1, when x is 1/2, now we're taking the 4th power of 1/2, that's 1/16. So to get how far this graph is above the x-axis, we've got to take the 1 unit, take half of that to get half a unit, half of that to get a quarter of a unit, half of that to get 1/8 of a unit, and half of that to get a 1/16 of a unit. So we see where this graph needs to go. Then, when we go to x to the 5th, and I didn't do a real good job of sketching that graph the first time, so I kind of smudged a lot of stuff out. Let's see if we can make that a little clearer. Okay. Anyhow, two things happen. One is, of course, if we take the 5th power of a negative number, we're going to get a negative number. And if we take the 5th power of 1/2, we get 1/32. So that the 1/32, we have to cut this into half, then a fourth, an eighth, a 16th, and cut that in half to a 32nd. We're going to be down here very close to the x-axis, and we go from the origin over to this point. The graph is almost flat, and it continues being fairly flat, and then it turns very abruptly and goes up. So that we get a graph that looks like this. So the x to the 5th graph looks a lot like the x cubed graph, but it's a lot flatter in this region here, and then a lot steeper beyond that. Now we could determine exactly where it becomes steeper, where this one becomes steeper than this one, if we knew calculus, but we don't know calculus. So you'd have to use calculus to answer that question. Either you'd have to be very clever. Okay, well anyhow, we see the progression then. We go from symmetry with respect to the y-axis to symmetry with respect to the origin, to symmetry with respect to the y-axis, back to symmetry with respect to the origin. And in each case between 0 and 1, the graph gets flatter and flatter and flatter, as we can see from these pictures. Well, these are all examples of the class of functions that we call power functions. So we're going to define that class and look at a couple of examples.